Hey, how? It's me, 11.4. Limits at infinity and limits of sequences. Horizontal asymptotes. Alright, first of all, I'd like everyone to check out page 780 because that's me, and that's super weird. I'm just leaning up against a dollar sign, wearing a spiked bracelet. Very strange. Anywho, um, what we talked about earlier is that there's two basic and really big problems in calculus. There's the tangent line problem and there's the area problem. So we talked about the tangent line and how that relates to derivatives. This time we're going to talk about limits at infinity and how that's going to relate to the area problem. So today we're really going to focus on limits at infinity, which is saying how does a specific function behave as it approaches infinity, which is kind of something that we've done before. We're kind of just going to do it in a more analytic way in terms of you know how does it approach when it approaches this arbitrary infinite value. What specific asymptote does it approach? Okay, so let's look first at this function x x plus 1 over 2x, and we can see it's coming down and it's kind of leveling out there. It's coming up and it's leveling out there. From the left and from the right, if I'm looking at this function, it seems to converge at 1/2. This horizontal asymptote of y equals 1/2. And we've seen that before and we've looked at it. But using limit notation, we can actually say that the limit of x as we look at it from the left side of this particular function will be 1/2, and the limit of the function as we look at it from the right side is 1/2, and we can denote it that way. So there's just again a little bit more notation to take in, and the definitions of specific limits at infinity. So if f is a function and L1 and L2 are real numbers, then the statements that the limit coming from the left of f of x is L1, and the limit coming from the entire infinity of f of x equals L2 denote its specific limits at infinity. Okay, so again, it's just notation. Now we have a couple of different new, almost intuitive rules, but just things to bring up just in case. Where if we have a specific function and an r value, which is an exponent in the denominator of that function, and that r value is positive, we essentially have 1 over an increasingly large number down here. Because if x is approaching infinity, this number is just going to be getting bigger and bigger and bigger and bigger and bigger and bigger and bigger. So eventually this is going to be 1 over like 10, 100,000 billion, gazillion, trillion, billion, gazillion, which is very, 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 very close to 0. It's not quite there, but it's converging to 0. Okay, so we can say that anytime that there's a singular number over this variable, which is approaching infinity on the bottom in the denominator, it's going to be approaching 0. So furthermore, if x raised to the r is defined when x is less than 0, then when we look at it coming from the left, then this entire thing equals 0. Now, why is that different? Well, it's basically the way that we're looking at it. If we looked at it as we're coming from the right, this entire function would be not approaching 0. It would be coming, if I were to draw this a little bit, it would be going that way. So if I look at it coming from the right, I'm not seeing that asymptotic behavior. I'm not seeing that limit. Whereas if I look at it from the left, I am seeing it converge to 0 in that direction. So that's why there's a little bit of a difference between these two things. Okay, so let's kind of move away from the theoretical, the formulaic part, and let's just work through a couple of these and see what happens. I want to find the limit of this as x approaches infinity. Okay, Well, let's see. I know for a fact from what we did before that if I have the limit of two things that are being added or subtracted, I can split those up. Alright, so I'm just going to do that first of all, and I'm going to say that this is going to be the limit as x approaches infinity of 4 minus the limit as x approaches infinity of this 3 over x squared. Okay, so that's cool, but now I also had another property that told me if I have two things that are multiplying, that I can split them up. This is really 3 times 1 over x squared. So what I'm going to do is I'm going to take this one right here and split it up. So it's just 3 times the limit as x approaches infinity of that 1 over x squared. So that's really cool. I have things simplified in such a way now that these limits are really easy to calculate. The limit as x approaches whatever of a singular number is just that singular number. 3 is 3, and I just said on the previous page that if I have a number with an x value in the denominator and a positive r value, as it approaches infinity, that's going to be 0. And just look back at that. That's this right here. That's set up for us right there. So we did have to kind of break it up and move it around to see that, but it is there, and that is a 0. 3 times 0 is 0. The limit here is 4. Okay, so if we keep in mind the properties of limits, that one's actually not too bad. And if we can try exercise 13, I think that you'll realize that using a couple of different tactics, it doesn't have to be too bad. Okay, so we can say that the limit of this particular function as x approaches infinity is 4. Now the next thing to talk about, and I know that, again, I said this every time, but this page is going to make you start weeping uncontrollable tears because of the notation. But before we start to freak out, let's just take it a step at a time. We looked at this notation earlier in the year, that a specific function that's a rational function is just some function numerator over some function denominator. Okay, that's all that this part is saying. And then the next sentence is explaining to us what n of x and what d of x are. N of x is, again, some polynomial that has a degree of n, and d of x is some denominator polynomial with some degree of m. Okay, so their highest degrees, respectively, are n and m. And that's going to be a little bit important because on the top, my highest degree is going to be an n. On the bottom, my highest degree is going to be an m. Because the next sentence really is looking at some rules that require that information. And it's saying that the limit of the function, the entire rational function, is going to be dependent upon what the highest degrees of the function's numerator and denominator are. So if the numerator of the top is less than the numerator of the bottom, the limit is automatically 0. Woo! Easy. I like that. I like that rule. All I have to look for is the degree of the top being less than the degree of the bottom, and I know my limit is 0. Cool. Okay, what about if those two degrees are the same? If I have x cubed on the top and I have x cubed on the bottom, well, it's just going to be a ratio of their coefficients. So let's say I had a function that on the bottom had, on the top had 3x squared, and on the bottom it had 2x squared, blah blah blah, blah blah blah. These are the highest degree values, they're the same, then the limit of this function would be 3 over 2. Okay, that's what that's saying. Now, if the top value is greater than the bottom value, the degree of the top is greater than the degree of the bottom, that limit does not exist. Okay, so this might actually be kind of reminding you of when we were talking about asymptotes for rational functions. We had 3 rules that were like this. If the degrees were the same, if the bottom was greater, if the top was greater, we had 3 different rules. So again, we have those 3 different types of rules that happen as well, and those are going to be helpful when we look at what the limits of rational functions are. So here we have an example of a rational function. It's just a little story saying that you're manufacturing greeting cards and they cost so much to make. You're going to invest $5,000, and this is kind of your formula for how much it's going to cost you altogether. And when we create a function that shows the average cost of a particular, of making these cards, it turns out to be a rational function, 0.5x plus 5,000 over x. So that's my function. And what I want to do is see what's the average price when I make 1,000 of them, when I make 10,000 of them, when I make 100,000 of them, and let's say that I'm going to keep going and keep producing, and I'm going to approach infinity. What's the average price as that goes on forever? So the first thing we want to do is just calculate at 1,000, 10,000, and 100,000. So I'm just going to plug in those values, really. I'm going to say, put in 1,000 here and here. The value I get out is 550. That's how much it's going to cost per card on average when I make 1,000. Put in 10,000. What do I get? Well, it's going to cost me an average of $1 to make all of them when it's 10,000 of them. And what about 100,000? Well, it's an average of 55 cents to on average to make one of them when I make 100,000 at a time. Okay, well, that's all fine and dandy, but what about when it approaches infinity? Well, when it approaches infinity, I have to think about my rules for the rational functions. I have to look at the degree of the top equation and the degree of the bottom equation of its leading coefficient. Well, they both just have x to the first and x to the first. So that means I need to look at their coefficients. I have 0.5 over 1. So the limit as x approaches this value off in the distance in infinity should just be 0.5. It should be 50 cents. So the more and more and more and more and more that I make, the closer I should be getting to 50 cents a card. And that's what this function is going to show me. It's going to show me that it's very expensive when I make just a few, and the more that I'm creating, the less expensive it becomes until we kind of level out at 50 cents a piece. All right? Hopefully that that idea it can sink in. It's not too difficult, and we can try exercise 57 on our own, and we can check in on that next time. Okay, and then the last thing that we're going to talk about in this section is the limit of sequences, which really is the same thing. We've looked at sequences and sort of almost a little bit looked at limits of sequences toward infinity. And I've been using this word today, converge to zero. And I'm going to use that word as well as the word diverge a little bit more when we talk about sequences and how they move in terms of infinity. But what this piece right here is basically telling you is that if you have a function that has a specific limit, and you have a sequence that can be written as a function, well, then that sequence's limit will also have the same value. Okay, so if I can create a function out of the series, it's going to have the limit that function would have. It's very, very simple and intuitive thing. It's almost like why are we bothering to write that down? But it's a more formal way of writing the limit of a sequence. And let's just show how this works. When I have this particular function here, I'm going to follow the exact same rules that I would have followed with the rational functions, and I'm still going to find the limit the same way. I'm just going to treat this sequence as a function. Okay, so this a of n, I'm going to treat it as a function, f of n. And I'm going to say, okay, well, what's the highest degree value here? I have n to the first, n to the first. Okay, so they're both the same, which means I'm just looking at a ratio between their values here. So I have 2 over 1 of their coefficients, so the limit of this one should be 2. Cool. What about b? On b, well, I have n squared on the bottom, I have n to the first on the top. That means my top value is less than my bottom, which implies to me I don't have to do any work. The limit of this one's going to be 0. And then lastly, on the bottom, I have n squared and I have n squared. They're the same, so I'm looking at a ratio between their coefficients, 2 over 4, 1/2. Is this true? Well, yeah, if I plug in a whole bunch of values, the first term, second term, third term, fourth term, all that, we're looking at all these things being and approaching to what I said that the limit was going to be. And if I put in a whole bunch of values and we go and we go and we go, well, I'm approaching 0, just like I was saying. And this one, as we put in values and we approach, we get to 1/2. Okay, so those rules are going to be the exact same thing. The vocabulary, again, with converging and diverging, all of these things are converging to specific points. As the sequences go on, they're getting closer and closer and closer and closer and closer, but never really touching. Convergence is very much like when you have an asymptote, and you can see where that asymptote is, and it's approaching the asymptote. It's converging to that point. The other word, diverge, would be, I kind of skipped over it back here. A sequence which does not converge is said to diverge, and that would be an instance of a sequence that does something like 1, negative 1, 1, negative 1, 1, negative 1, on and on and on and on and on. It's never going anywhere. It's just constantly flipping back and forth and back and forth. It's not getting anywhere, and it's not approaching any specific asymptote. So that's a divergent sequence, and it's just two different things to take a look at and to be able to identify when you're looking at those things. So the last thing that I would like you to try out is, if I can write this on here, exercise 43. And once you're set with that, I think that we'll be in a pretty good place where we can come into class and just rock it. It's gonna be great. I will see y'all in a bit. Peace out. Keeps it real. It's all about the Benjamins. So I'll be talking to y'all's later. Bye bye.